Chemistry, Unit 3, Production by Electrolysis. In this session, we will talk about one particular case, which is the expensive one. That is, we are electrolyzing a molten liquid. Okay. So, electrolysis of molten liquids. So for electrolysis, basically it refers to a process where we use electrical power to force a reaction to happen. Normally we're forcing a non-spontaneous reaction to happen. Then an electrical power is converted to chemical energy in this when we are going through electrolysis. So if we are going to use electrolysis for production, we normally use it to produce something that's very, very reactive. So many substances, reactive substances, for example, aluminium metal or sodium metal, they naturally exist as compounds like aluminium oxide or sodium chloride. Unlike those inert substances, for example, gold metal or even platinum metal, because they're so inert, they naturally exist as metals when you mine them. But for those reactive metals, they're already combined to other substances in nature, so they're always mined in their compounds. If we are going to extract them from their compounds, we have to use electrolysis. Okay? We can reverse the reaction that makes them, and so as to obtain them in their elemental form. Now, how do we do that is we take sodium chloride, for example, and we take your normal household table salt and melt it into a molten sodium chloride electrolyte. Okay, it's not a solution, it's just a melted ionic liquid. Okay, so you would know that this forward reaction is not going to happen spontaneously. Otherwise, on your dining table, you will have a lot of chlorine gas surrounding you. Okay, so this reaction is not going to happen spontaneously, and as a matter of fact, sodium chloride is so stable that we have to apply extreme measures. That is, apply a lot of energy to force it to decompose. You notice that the state for this electrolytic reaction is I put liquid for both sodium metal and sodium chloride. That is because we are electrolyzing a molten sodium chloride, so it is already liquid, and because the temperature to melt this ionic compound is going to be so high, as a result, the sodium produced will also be liquid state. Okay, and chlorine will always be gas. So the power source is provided, and then it's injecting electrons into this particular electrode. And as electron arrives here, the sodium cation in this molten chloride electrolyte is attracted by the negative charges of the electrons, and then it travels to this particular electrode and goes through a reduction reaction, becomes sodium metal in liquid state. Okay, so pay attention when we are electrolyzing a molten liquid. Your states have to be reflecting this special environment. Okay? On the other hand, the chloride ion in the molten electrolyte will be attracted to the positive end of the power supply. So they'll go to this electrode and gives out its electron, so donate its electron, and the electrons can then travel back to the positive end of the power supply. So as a result, the other electrode will be the anode, where chlorine gas is formed. Okay? So during electrolysis, the reactants, so our real reactants here are sodium cation and chloride anion, as you see in these half equations. Okay, so sodium cation and chloride anion are going through reaction. These two can coexist. They are not going to react spontaneously. However, their products, sodium metal and chlorine gas, can have a spontaneous chemical reaction. So it is very dangerous if these two are meeting each other. So just like in all other electrolysis process, the products of electrolysis are always going to react spontaneously, and as a result, the products of electrolysis must be separated. Okay, so let's go through it again. Anions oxidized at the anode, because oxidation happens at the anode. So chloride come here to be oxidized, and then cations are reduced at the cathode, which is connected to the negative end of the power supply. Electrical energy in this process is converted to chemical energy through a non-spontaneous redox reaction. Water is not present here whatsoever. If it is present, it will interfere with this particular reaction. We will talk about that in later sessions. But the implication to you is that when you are writing half reactions with states for electrolysis of molten electrolytes, you must make sure that your states are correct and reflecting the environment. It is not just the states that you can copy off from your data book. Electrodes, in this case, when we are electrolyzing the molten liquid, it must be inert. By inert, I mean not only do they not react with the molten electrolyte, but also they cannot react with the products that's being produced. As you know, when we reverse the spontaneous redox reaction, our reactants are going to be very reactive. So your electrodes must be very, very inert. At the same time, products must be collected separately, because if it don't, they have a spontaneous redox reaction right there in that electrolytic cell. That totally wasted all the energy that you have put in. Okay? And since it is a molten electrolyte, it requires a lot of energy to keep things molten. Just think about if it's by no means easy to melt a sodium chloride solid, and to keep it in that liquid state also again requires a lot of energy, and therefore it is very expensive, energy consuming and expensive. So we only use this technique to obtain the substances that we really can't obtain in any other way.